so there is although one section on nonlinear time series analysis and recurrence networks. So I will try to cover this nonlinear time series analysis, recurrence networks, and complex networks in today's class. So next week, Dr. Rajiv and Bipin, they would be taking. So Rajiv would be talking about self-organizing maps, and Bipin Kumar will be talking about downscaling. So next week will be completely by them. Yeah, so deep learning for downscaling. And okay, so I want to start by showing you a paper. So um, this is the title is Analysis of Spatial and Temporal Extreme Monsoon Rainfall over South Asia using Complex Networks. So in this paper, what they have, so this is by Nishant Malik et al. And so what they have done is that they take the rainfall dataset, the 90th and 94th percentile rainfall events of Indian summer monsoon, June to September, and they analyze the monsoon from a complex network perspective. So this is the topographical map of the Indian peninsula with of the and the Himalayas. So you can see, and they first they basically construct this kind of, so alpha equal to 94 and alpha equal to 90%. So these are the different threshold percentiles, and so we note that generally high daily rainfall amounts in the Ganges plain and at the orographic barriers. So yeah, and then they apply this framework of nonlinear uh, method, the complex network, and what they do is they construct these maps. And I will, yeah. So they ultimately what this is the output of their work, wherein they are able to see that in the spatial domain, which region is controlling how much of dynamics. Okay, so these are the four important regions that they find out: North Pakistan, the Tibetan Plateau, the Central India, and the Western Ghats, and how much of an influence that these regions have over like over a larger area. So you can see that Central India has a very localized control, and this is also, I think, the reason why this it's safe to take this as a homogeneous region. And you can see similar for Tibetan Plateau, Western Ghats, but this North Pakistan, this has got a large like it's, you can consider this to be like as you have a string, and um, a ball is or a stone is connected to it, and you are basically rotating it and how far it can go. So these are the different network metrics that they have computed. So we will start with the complex networks. Okay, so what are complex networks? So like we have some aspects of these kind of networks are similar to graphs, and that we have seen in the introduction to graph neural networks also, the nodes, the edges, the graph as a whole. So there are some these are some examples. These are some examples of the complex networks. So internet is one example, and then we have the World Wide Web. So, and then there is HTTP network, telecom networks, routes of airlines, and Usenet, VLSI circuits, biological networks, swarms and flocks, human relationships, arts, and they all basically come under this the purview of graph theory. So can one walk across all the seven bridges once and then return to the starting point? So that's those are the kind of questions that people would typically ask with these kind of graphs. And then there are I don't think we need to go into this detail. So network is a graph with a set of nodes interconnected via edges. And there are networks in different fields like computer networks, neural networks, social networks, and you can have these different topologies of the networks. So okay, we will see. Yeah, I think that's about it. So for performing for doing this the complex networks on climate science or on weather and climate science datasets, there is this library known as PyUnicorn. Okay, so PyUnicorn is a fully object-oriented Python package for advanced analysis and modeling of complex networks. So you can directly use this library for performing this kind of nonlinear time series analysis in Python. But before going to PyUnicorn, I will show you this paper. It's a very nice uh, compilation of the entire nonlinear time series analysis and the field of recurrence plots. So this is by Bedartha Goswami. And okay, so nonlinear time series analysis is like it started somewhere around in 1980s, and primarily because of its ability to characterize, analyze, and predict non-trivial features in data sets that stem from wide range of fields such as finance, music, human physiology, cognitive science, astrophysics, climate, and engineering. And more recently, recurrence plots initially proposed as visual tool for analysis of complex networks have proven to be a powerful framework to quantify and reveal non-trivial dynamical features in time series data. So this tutorial review provides a brief introduction to the fundamentals of nonlinear time series analysis before discussing in greater detail a few approaches of recurrence plot based analysis of time series. In particular, it focuses on recurrence plot measures which characterize dynamical features such as determinism, synchronization, and regime changes. We'll discuss what are these terms. And the concept of surrogate based hypothesis testing, which is crucial to drawing any inference from data analysis, is also discussed. Finally, the presented recurrence plot approaches are applied to two climate indices related to the equatorial and North Pacific regions and their dynamical behavior and interrelations investigated. So for that, okay, so we will, okay, this is some basic introduction. Now, okay, this is the bar plot of the number of, so this is with keywords as nonlinear time series, and this is with the recurrence plots. So and how frequently they occur in the all fields, and in title we can see that there is a general interest in increasing interest in the fields. So before okay, I think I have discussed this before, but before going through this entire thing, we need to see what is Taken's embedding theorem. Okay, so okay, so Taken's theorem in is the 1981 delay embedding theorem of Floris Takens, provides the conditions under which a smooth attractor can be reconstructed from the observations with a generic function. So think of it like this: you have a multi-dimensional time series, or For example, if you have studied the Lorentz system, okay, or Lorentz attractor. So this is the Lorentz system, right? Now Lorentz system, basically this has got it's a solution of these three equations: dx by dt equal to sigma y minus x, dy by dt equal to x into rho minus z minus y, dz by dt equal to xy minus beta z. So you start with some values, some constant, rho, sigma and beta, and then you start with some initial conditions. So what you will get is this kind of a plot. Now what this is basically you are solving for x, y and z at every time. So you are integrating forward in time. So at time equal to 0, you, let's say you start with 0 0 0, and then at time t equal to t plus delta t, you can solve for xyz. So for at every time you will get some corresponding value of x, y and z. Now these x, y and z you can plot on a three-dimensional axis. So that looks like a butterfly curve, and this is the famous Lorentz butterfly curve, and this has got these two attractors. So why we are calling them as attractors is because the dot that you see is we call as the state of the system. Now why we call it as the state of the system is because it is uh, it is basically the location of the system, or the location of the uh, Lorentz equations at a particular time in the space, or what we call as the state space plot. So this is known as the state space plot. And at every time, at every point on this plot corresponds to a particular time, okay, and that is known as the state of the system. So this one you can also plot it as so you can also plot, so this is a three-dimensional visualization of the Lorentz equations. You can also plot it as three time series, okay. So yeah, so these this thing this is a this is in the space domain, and whatever it is moving is in time, right? Now this is having x-axis is time, and the in the y-axis you have three plots. So these are the three x, y and z variables of the Lorentz attractor, and these are what I am talking about. So if you draw a vertical line here, at every time you will get a particular value of x, y and z, right? Or y1, y2 and y3. And you can have a three-dimensional uh, axis, and you can just plot this Lorentz system, and you will get this Lorentz attractor. So I hope that this is clear, right? The What is the state of a system, what is a state space plot, what is a Lorentz system. Now comes the Taken's embedding theorem. Okay, so okay, one more thing is that, okay, so these are we have three variables here, right? So we say that this is a three-dimensional system, okay. But for example, now you consider that you set up an instrument in the in IITM, right? And you start measuring something, let's say temperature, and you get this kind of a time series. So you are measuring the temperature at different points of time, and you are measuring that temperature, but or you are measuring some field that you don't know. Now that might be a combination of so many different factors, right? That for example, it's an urban area or a rural area, how the wind is blowing in that region, how the vegetation is. So it can be a combination of the n dimensions or n number of variables, right? But you are measuring only one. Okay, so but then to analyze or to understand the system completely, you need to measure that system or that state space in an n dimensional framework, but you are basically restricted by the instrument that you have, or by logistical challenges. So what we do is we take the rescue of this theorem known as Taken's embedding theorem. Taken embedding theorem, it tells us that given a single time series, you are given, let's say you are given just this single time series, you can reconstruct the n dimensional state space system. So just with one single time series, you can reconstruct the other two. Okay, how to do that, we will see. So is Taken's embedding theorem clear?
Yes, sir.
Okay. So this was by Taken, and it offered it was not clear how to infer the details of the high dimensional system. So the thing is, like, why I discussed those concepts with you was because if you read this paper, you will have to go lot of times, you have to back and forth, you have to go through the references to completely understand, because I believe that not many people by default understand what is a state space system or what is a state of the system. So we'll read this. It was not until the 1980s, however, that the theoretical developments of nonlinear dynamical systems began to give rise to new time series analysis techniques. This was primarily because most real world time series were one dimensional scalar measurements. So this is what I was talking about. Uh, for example, you are just measuring single variable, single field, which is a scalar one dimensional measurement. You are just having a time series, which in the nonlinear dynamical viewpoint were the projection of a high dimensional time evolution onto a real number, onto the set of real numbers R by a measurement function. So it was not clear how to infer details of the high dimensional dynamics in the true state space of the system from the scalar valued time series measurements. So it was you just have a time series, how to infer the n dimensional statistics or the true state space of the system from that single time series. And two papers, one by Packard et al. In 1980, another by Takens et al. Takens in 1981, offered possible solutions to the problem and in essence gave form to the discipline of nonlinear time series analysis as it is formulated today. So the task of inferring the high dimensional dynamics from a scalar time series is called state space reconstruction, became the cornerstone of nonlinear time series analysis. And from the 1980s, along with the further development of theoretical phenomena such as self-similarity and fractal dynamics, strange attractors, bifurcations, and chaotic synchronization, there was an increase in the number of studies that applied these concepts to the time series obtained from laboratory experiments and real world data. So you can have these time series from either lab experiments, or you can have from the real world data, and you can apply these theories of these analysis techniques of nonlinear time series analysis to the to the lab experiments or the real world data sets. And the boom in nonlinear dynamics related studies is also attributable to the parallel development of increasingly faster, more compact, and more powerful computers. The 1990s witnessed a drastic increase in the number of studies related to nonlinear time series analysis. Nonlinear concepts began to be increasingly applied to complex systems from fields such as population ecology, human physiology, and climate. So these are the papers that we have already seen. And in 1987, Ekman, Campost, and Ruel proposed a new graphical representation, the recurrence plot. Okay, so what is a recurrence plot? Okay, so let us see from this website. It's called recurrenceplot.tk. Okay, and this is something which was like a lot of work has been done by Norbert Marwan and others. So yeah, so it says that the definitions of recurrence plot, it says that a recurrence plot is an advanced technique of nonlinear data analysis. It is a visualization of a graph in a square matrix in which the matrix elements correspond to those times at which a state of the dynamical system recurs. Okay, so this is very important. At which the state of the dynamical system recurs. So what is a dynamical system? Now this Lorentz system is a dynamical system, right? Dynamical system is anything which has dynamics, changes in time. Okay, so this is a dynamical system, and from the definition of, okay, where is it, man? Ah, yeah. So recurrence plot is a visualization of a square matrix in which matrix elements correspond to those times at which a state of the dynamical system recurs. So technically, a recurrence plot reveals all the times when the phase space trajectory of the dynamical system. What is a phase space trajectory? Phase space trajectory is nothing but the trajectory of, like, this is the phase space trajectory. These lines that you are seeing, these are the phase space trajectory of the dynamical system. So they say that reveals all the times when the phase space trajectory of the dynamical system visits roughly the same area in the phase space. Okay, what is a phase space? This entire thing, the superset is the phase space. So this you can also call it as a phase space plot. Okay, yeah. So yeah, before going to the visualization, I'll just read this first. And natural processes can have distinct recurrent behavior, example periodicities, but also irregular cyclicities. Moreover, recurrence of states in the meaning that states are arbitrary close after some time is a fundamental property of deterministic dynamical systems and is typical for nonlinear or chaotic systems. The recurrence of states in nature has been known for a long time and has also been discussed in early publications. So Ekman et al. Have introduced a tool which can visualize the recurrence of states xi in a phase space. Usually a phase space does not have a dimension 2 or 3 which allows it to be pictured. So think about it like this. Now this is something. Now human eye can see only 3 dimensions, right? And in the fourth dimension we call it as a time. So we are experiencing the time and we can actually see the 3 dimensions. But what if a system is more than 3 dimensional? What to do about that? How would you analyze that? How would you visualize that? This one, we saw that it is having these 2 circles, so we say that this is got these true two attractors. But what about a system which is 10 dimensional, or which is 20 dimensional? It's, you cannot visualize that, and you cannot see what's going on with that system. But what you can do is you can construct recurrence plot of that n dimensional system. Okay, so and recurrence plot is a tool which was introduced by Ekman et al. And it can visualize the recurrence of states in the phase space. Okay, and usually a phase space does not have a dimension which allows it to be pictured. Higher dimensional phase spaces can only be visualized by projection into 2 or 3 dimensional subspaces. However, Ekman's tool enables us to investigate the m-dimensional phase space trajectory through a 2-dimensional representation of its recurrences. And such recurrence of a state at time I at different time j, so marked within a 2-dimensional squared matrix with ones and zero dots. So what is this? For example, you have this phase space plot, and these are the trajectories, right? So in this phase space plot, what you have is okay, yeah. So what you have is, for example, you have these 2 points, right? So you have these two trajectories which are moving very close to each other, right? So we define an epsilon. Okay, we say that this is a very small number, and uh, two uh, two states in the system, when they are at a distance closer than, which is less than the epsilon. Okay, so we say that that is like we consider that to be the same state of the system. Do you understand that? So for example, x x I, so this is at time I, the system is here. Okay, let's say this is at time I, and the second guy is at time j. Okay, and the distance between them is xi minus xj, and if it is less than epsilon, okay, so then if it is less than epsilon, we call it as the same state of the system. And if we find that is the same state of the system, what we do is, on the x-axis we construct the recurrence plot in a way that on the x-axis we have time, okay, and on the y-axis also we have time. So corresponding to these two sets of times, let's say I is 5, j is, let's say, 11. Okay, so 5 comma 11 we will see here, and if it is the same state, we will put a black dot. Now black dot means it is, we will just give in the matrix, we will just put a 1. Okay, and wherever you see empty, it is these are all zeros. So here important feature to note is that you will always get this diagonal line, because corresponding to this diagonal line you will have like the state at 2 comma 2, so x2 minus x2, so that is always the same state, right? So you this is what you get is known as the recurrence plot. Okay, and recurrence plot you can basically construct for any n dimensional system. It doesn't have to be a 3 dimensional like a Lorentz system, and you can see some kind of patterns here in this recurrence plot. So it can be seen that although the system is chaotic, but it has some predictability, right? So there are there are patterns which are recurring after some point of time. Okay, so these are the patterns which are recurring, and hence this has got a predictability if you can identify those patterns. And these are what is known as the structures in the recurrence plot. So there are different type of structures that can be found in the recurrence plots. So the first one is called as homogeneous. Homogeneous is this one. Okay, so this is for the uniformly distributed noise. Let's say you have some noise time series, and you construct a recurrence plot out of it. So it will look like this. Okay, now this doesn't look like or seem like having any pattern in it, right? Now then you can have periodic oscillations. So for periodic oscillations, this is some particular type of, let's say, sine x plus cos x or something like that. You can see that for periodic oscillations you can see this kind of superposition harmonic. So this kind of structures, proper structures in the recurrence plot, which are which are representing that there are this it's a periodic system with defined certain frequencies which are superimposed on each other. And then you can have something as drift. So logistic map is also similar to Lorentz equations. It is also a set of equations, and here its recurrence plot looks like this. Now this is not noise, okay, but still it has got some patterns. And then you have for Brownian motion, you can see that this is the recurrence plot. So this is like quite non-linear, but there are these patterns which are recurring in the recurrence plot. Okay, so that is about the basics of recurrence plots. We'll come back to this tutorial paper. And okay, so several methods were put forward to quantify patterns in the recurrence plots. Example, diagonal line structures to infer probable dynamical features, such as high degree of determinism. So we will see what is determinism, but just think about it in terms of predictability. Okay, so I was talking about predictability, that a system is more predictable, and the approaches based on recurrence plots are collectively referred to as recurrence quantification analysis. So we were when we were seeing these recurrence plots, this was just a visual inspection, right? But you need to quantify and you need to come out with some numbers which basically tell you in a quantitative manner what like what is it that the recurrence plot is showing. So that kind of analysis is known as the recurrence quantification analysis, and they form a core of the recurrence plot based techniques. A crucial advantage of recurrence plot based approaches over other nonlinear approaches is that they perform reasonably well even when the length of time series is short. So even a 50 to 100 data point time series is enough for a recurrence quantification analysis. And moreover, in the cases when underlying system is not sufficiently deterministic or stationary. So what is a stationary system? uh, does anybody know what is a stationary system? A system whose mean does not change over the over time, right? So that's a stationary system. And so recurrence plots have proven useful in characterizing their behavior. So we will, yeah, these are some examples of how they would use these recurrence plots. Okay, so yeah, these are some basics of what is a dynamical system and what are attractors, what are bifurcations, state space reconstruction. So measurement paradigm and the time delay embedding. So how would you so given a time series, okay, so how would you embed it into an n-dimensional n-dimensional state space? Okay, so first of all, what you have to do is you have to find out something known as the time delay parameter. Okay, so it is known as the time delay embedding. And for time delay embedding, what you do is there are different techniques of doing this. Okay, so one is you can find out the self mutual information, and so at different delay, so you have a particular time series and you create the other time series by delay parameter tau. So you just shift the time series by tau equal to 1, tau equal to 2, tau equal to so 3, and so on. And for those shifted or delayed time series and the original time series, you find out something known as the either the mutual information or maybe the false nearest neighbors. So why false nearest neighbors? So uh, I will just show you the false nearest neighbors. Okay, so you should basically understand the concept of false nearest neighbors from from this kind of a spatial example. Okay, so for example, you have you just have a single time series data, right? You measure the data just along this axis, you will get these 3 points. Okay, and you might think that these 3 points correspond to the same dimension or the it is in the same axis, right? But when you It might not be true, because if you just rotate the system, if you just rotate this, like this is like you are just seeing it from a perfect 90-degree angle. But if you just rotate it, or you just see it from the top, you might see something like this, right? So then you will realize that this point X, this point, this green, red, and blue, they are not uh, they are not on a single dimension. It's a, when you might think that this is a two-dimensional system, okay? But this was seeing it from just from like as a 90-degree view. This seemed like a neighbor of these 2 points, but this was a false neighbor, right? So this is a false nearest neighbor. And if you again further rotate the axis, you might even see that this is a three-dimensional, like although these 3 points are not on a three-dimensional system, but you might see something like this. If some point was here, and you will visualize it to be as a false neighbor, right? So that is the idea behind doing the false nearest neighbors. So you have to find out uh, the percentage of false nearest neighbors. Okay, I will just do this. So you have to find out the percentage of the false nearest neighbors, and at the different embedding dimension. Okay, so you have to check at different embedding dimensions, embedding dimension 1, 2, 3, 4, 5. So at the embedding dimension at which you get a minima over the false nearest neighbors, that is your embedding dimension of the system. Okay, so how we do that is, so finding out the false nearest neighbors and embedding dimension, you will need this, the time delay parameter. And the time delay parameter you will get using self mutual information or autocorrelation. You will have to do between the lagged time series at different delay parameters, and the first minima uh, is basically chosen as the time delay parameter. So is that clear, how we will find out the time delay parameter and how we will choose the embedding dimension? And yes, no, okay,
Yes, sir.
okay. And then so then you will basically so once you are clear with the time delay parameter and with the false nearest neighbors, so for the corresponding time delay parameter, so for example you have a time series as okay, so I will just show as an example. So if you have, let's say, this time series, okay, 1 2 3 4 5 6 7 8 9 10, okay. So this is the time series that you have now, with a time delay parameter as 1. Okay, so the time series, the second time series will be 2 3 4 5 6 7 8 9 10. Now in this time series with a time delay parameter as 1, okay, the first, at the first time, the number that you have is 2. So 2 here corresponds to 1 here. Okay, so although the length of this will decrease, so what we would typically do is we will keep reducing, we will keep eliminating the last element from the original series. Okay, and at time delay parameter 2, you will get this series, right? And then you will also remove the last element of the original series. So then you will find out some metric between these two time series. Okay, at now this is at time delay equal to 2. Okay, so that's what we were seeing, right? So at time delay on x-axis, uh, you will, on the y-axis you will find out some metric, like, okay, you can find out, you can take the correlation between them. That becomes the autocorrelation at tau equal to 2, or you can find the mutual information. Now after finding out the time delay, the correct time delay parameter tau, and the embedding parameter m, Okay, let's say the tau that you got is equal to 2 and the embedding dimension that you got is 2. Okay, so in that case, what you will basically do is, so you just have a two-dimensional series. So these will be your two series, right? Now, but let's say if you get the embedding dimension as 3, so what you will do in that case? So what you will do is you will create three series. Okay, at so first of all you will create three series which have a time delay parameter of 2. Okay, so first you start, this is your original time series 1 2 3 4 5 6 7 8. Then you have at time delay equal to 2 you have 3 4 5 6 7 8 9 10, right? And then you will have 5, sorry, you have 5 6 7 8 9 10. Okay, so now this is these three form your, so let's say you are given just in the Lorentz system you are just given x. So now you have found out x, y and z, and now if you will plot these x, y and z in the three-dimensional state space plot with just one single time series, and after finding out the time delay parameter, doing the embedding, Taken's embedding theorem, what we find out is that we get a similar phase space plot, and which is what was theoretically told by the Taken's embedding theorem. So is that clear? So this is how you will basically you will create or you will embed the a single time series using time delay embedding in practice. Okay, so once you have done that, so you can, what you can do is you can very easily construct the recurrence plot. So within the recurrence plot, now at every time what you have is basically a vector of dimension, whatever dimension you have, right? So if you have a dimension as 3, right, every time step you have this vector of size 3, right? So you can use some kind of metric, either L2 norm or L1 norm, and then you can find out the distance uh, between the two states, and it can be in any dimension. It can be even 10 dimension, so that it will correspond to these. If it is 10 dimensions, so this will be a 10 dimensional vector, right? So that is about recurrence plot. And now with these recurrence plots, what you can make is known as a recurrence network. So what is a recurrence network? Recurrence network is nothing but you consider the recurrence, the matrix of recurrence plot as an adjacency matrix of complex network or a graph. So you remember, right? Adjacency matrix of a graph, A is nothing but it is a matrix of zeros and ones, where on x-axis and on the y-axis we have the nodes, right? We have all the nodes, so which you can represent as a graph or you can represent as an adjacency matrix. Now this recurrence plot or recurrence matrix can actually be considered as an adjacency matrix. Okay, and once you do that, you can you can you can construct a graph of an or a network out of it, and you can call it as a recurrence network, right? So you can do quantification of the based on the different recurrence patterns. So one is so the first quantification recurrence quantification metric is known as determinism. So what is determinism? Determinism is basically the it's the how many of the diagonal lines you are finding out in the recurrence plot. Okay, so more the determinism, more your system, you can say that it is more predictable, right? So how you can use this is depends on you. You can have different time series, and and you can find out which of these time series is more predictable or which of these time series is less predictable. Okay, then you have the average shortest path length. Okay, so path between two nodes I and j in a network is defined as a sequence of nodes that need to be traversed in order to go from node j to node I, right? So this is the average. So you take the path length between all the nodes in the network, and the average of the path length is known as the average shortest path length. So then there are other metrics. Yeah, they have not explained here. We will see in pi unicorn. So using pi unicorn, you can easily create a recurrence network. Okay, so here what they are doing is they are basically loading the n7 time series data set, and what they are saying is that on the spatial map, okay, on the spatial map, every point or every grid point, it corresponds to a node in the complex network, or what we call as the climate network. And it has got every time it's got a time series, right? So you can create an adjacency matrix based on its the relationship of a point in the in the mm, in the on the map, uh, the relationship of a point or a grid point to another grid point based on some metric, which can be either correlation or it can be any other thing, and you can construct the adjacency matrix. From the adjacency matrix you can construct the complex network or the climate network, and you can get these metrics of quantification analysis. So degree, one of the most important of them is called degree. Then we have closeness, betweenness. So degree is basically, I will open this paper if I can. Let me see. So this was actually first shown by Sonis in 2004, the architecture of a climate network. Oh, this is closed. Okay. Well, let us see if we can open this. No. Yeah. So here, what you can see is, okay. So on this map, this is they are using the gridded data set, and every grid point in the data, it is considered as a node, and a complex network is constructed, and on the top it is saying total number of links at each geographic location, and on the bottom it says same as top but the number of links with a distance of at least 5,000 kilometers. Okay, so this is the number of links. And okay, yeah, I think that's it. This is the first paper. So you can go ahead and see what is the degree centrality. So these are known as the different recurrence, the different measures of it must be there in the Malik's paper, the degree centrality. Okay, yeah, so these are the different complex network measures. Okay, so degree centrality is basically the number of nodes on an average that that a node is connected to in a network or in a graph. Okay, then we have something known as the betweenness centrality. Okay, betweenness centrality is nothing but for example, you have three nodes 1, 2 and 3. So if the connection of 1 and 3 passes between two, so that is considered as a valid connection or valid betweenness centrality for two. So betweenness centrality is the measure of how many paths connecting two different nodes pass from a particular node. So that is the betweenness centrality. And then there are other metrics. Okay, yeah. So that is about the complex networks. And then there is this thing known as surrogate based hypothesis testing. So what you can do is that from the recurrence plots, okay, from the recurrence plots, what you can do is, so there was a method which was constructed, which is called as the uh, twin surrogate method. Okay, so for example, you want to perform a robust statistical significance estimate of a particular index that you have computed, right? For example, you have two variables or two time series and you have computed, let's say, correlation over them. I'll give a very simple example. And what people would typically do is they would find out from some kind of distribution the 95th percentile confidence from the, I think, the t distribution. But those kind of hypothesis testing, it assumes that your underlying distribution is normal or it is having some kind of a uniform distribution. But actually that might not be true. Your data might not be a normal distribution or it might not be a uniform distribution. It might actually be highly non linear in nature. So how to basically test the like whether your results are statistically significant or not in that case? So what you will do is you have these two variables, right? X1 and X2. You will construct some kind of surrogate time series. Okay. So 100 or 1000 surrogate time series of X1 and X2. And for those time series corresponding, like for each pair, you will compute the correlation. Okay. And then for you get the 1000 correlation coefficients. Now you will find out the 99th percentile or the 95th percentile of those correlation coefficients. And if your original correlation coefficient is greater than the 99th percentile or the 95th percentile, then you can say that your result is statistically significant at 99 or 95 percent confidence. Okay, so that is the idea of surrogate based hypothesis testing. It's a very it's a state of the art hypothesis testing technique. So for generating those surrogate time series, there are methods. Okay, so there are methods known as so I'll show you surrogate time series. So it is also available in PyUnicorn, but PyUnicorn twin surrogates is not accurate. So I'll show you how to do that also. So first, people, what they came up with was called as the Fourier transform based surrogates. So they said that, okay, so you are generating a surrogate time series. Your surrogate time series should have the same Fourier spectra as the original time series. But then later on, after this Fourier, like people found out some kind of deficiencies in this Fourier transform based surrogate time series generation. Then what they proposed was known as the amplitude adjusted Fourier transform. So the amplitude or the actual values of the surrogate time series should be similar to the original time series. There were some issues with that also. So then they came up with something known as the refined amplitude adjusted surrogate time series. So it says that a set of amplitude adjusted Fourier time series surrogates is iteratively refined to produce a closer match of both amplitude distribution and power spectrum of the so the amplitude distribution is also taken into care. And then okay, then there was something known as the white noise surrogates. So it just returns a shuffled copy of the original time series. And then the state of the art in the surrogate time series generation is known as the twin surrogates. Or the so this twin surrogates was the basically introduced by Thiel in 2006 and Marwan in 2007. And in twin surrogates, what you basically do is you construct a recurrence plot of your time series, and from the recurrence plot, let's say this is the recurrence plot. So if you have like a time series of 50 numbers, right? So now you first find out something known as the twins. Now, what are twins? Twins are basically states which are very close to each other in the recurrence plot. So that you can find very easily because we set some epsilon and we say that there are these two states which are very close to each other. So we classify them as twins. So we just mark a lot of twins on the recurrence plot, right? Now you start from some random numbers. Let's say you start from the 26th number, okay, in the time series. Now you have to create a surrogate time series which has to be of the length same as the original time series, so which is having a length of 50. So it is like, so you will start at 26, so you'll go 27, 28, 29, and you will wait until you encounter a twin. Okay, so once you encounter a twin, let's say 31st number is a twin, what you will do is you will hop off. Okay, so what I mean by hopping off is, so let's say this state is basically oscillating around the state space attractor, and you find out that at this point there is a twin. So if you wherever you find twin, uh, like you hop off to the other trajectory, okay, and then you keep on adding those numbers, keep on appending those numbers to the surrogate time series. So you do this for 100 or 1000 times, and then you get the twin surrogate time series, so that which basically preserves the nonlinear properties of the system. So that is about the twin surrogate analysis and twin surrogate time series, and this is an application that they have shown. So based on this paper, okay, so based on this paper, there is a library, nonlinear time series. Yeah, so you can go and see this library or this repository, NLTS vibration, okay, and you can find all the codes here. And the so all the functions or all the things that I discussed today, so you can find in recurrence.py. Okay, so how to find out the mutual information, the entropy, 1D entropy, 2D entropy, the first minimum, and then the autocorrelation function. So we discussed that for finding out the time delay and embedding, either you can do a mutual information or autocorrelation. How to find out the false nearest neighbors? So you just have to give a time series X, you have to give a tau time delay embedding, you have to give the maximum dimension up to which you have to test it, and this will give you the false nearest neighbors, minimum distance, how to embed a time series into an n-dimensional state space system. This will return the recurrence plot for you. This function will return a recurrence matrix. So given a time series and embedding m, m is the embedding dimension, tau is the time delay parameter, e is the epsilon. and what is the norm that you want to use, either you whether you want to use the Euclidean norm or any other norm, and you threshold by what metric, or whether it is distance or whether it is fan or FRR, and then you have the normalize, and here you have the surrogates. Okay, so to generate the amplitude adjusted Fourier transform surrogates, or whether you want to generate the twin surrogates, okay, or whether you want to generate the correlated noise surrogate. So you have all these things here. So that's it about like what I wanted to discuss for nonlinear time series analysis and complex networks. So if you have any questions